Now we're going to look at a couple of specific types of force, drag force and friction force. First, let's think about drag force. The drag force, say, for a specific example, felt by something that's falling through the air. So something falling while it's feeling with a drag force. The important point to remember about a drag force, whether it's a drag force on something moving through the air or something moving through water, either way, the strength of the drag force depends on the speed of the object. Higher speed means stronger drag force. And depending on a lot of different factors, the magnitude of the drag force might be just proportional to the speed, the magnitude of the velocity, or the magnitude of the drag force, the strength of the drag force might be proportional to the square of the velocity. But either way, as something speeds up, the drag force on it is stronger. So when an object falls and speeds up, the drag force will get stronger as time goes by. If you just drop a rock, the instant you let go, it's still at rest. So at the instant you let go, say that's the moment when you turn on the stopwatch, time is zero, and since the velocity is zero, there's not yet any drag force. If this is zero, drag force is zero. So the only force on it is the weight, mass times acceleration due to gravity. The only force on the rock is the weight, so the net force is just the same as the weight. Now you wait a little while, the rock has accelerated a little bit, it's gained some speed, so now it has drag force that it didn't have before. The force pulling down, the weight, is still the same. That doesn't change. It's always mass times g. But now there's a little bit of a drag force opposite to the velocity. And so that bit of drag force cancels out some of the downward force so that now the net force is smaller than it was before. But there's still net force down, in other words, net force in the direction of motion. So as the rock falls, it's still being pulled in the direction in which it's moving, so it's still going to speed up a little. And as long as it continues to speed up, the drag force gets stronger. If the speed gets higher, the drag force gets stronger. So you wait a little while until time 3, a little while after time 2, the rock has had a chance to speed up some more, so the drag force is even stronger. That means it cancels out even more of the downward force, the weight, so there's even less left over to be net force. As the drag force gets stronger, the net force decreases. Until finally, wait until a fourth time, a little bit later after this time, there's still force pulling the rock in the direction of its motion, so it's still speeding up a little bit. And so the drag force will continue to increase a little bit, keeps on increasing until at one point it's increased enough so that the magnitude of the drag force is the same as the weight, m times g. And now you've got equal amounts of downward and upward force, so the net force is zero. And of course, Newton's second law tells us that if there's no net force, there's no acceleration, because it's net force that causes acceleration. And if you don't have acceleration, you don't have if you don't have net force, you don't get acceleration. So at this point, when the drag force is increased so that it entirely cancels out the downward force, the weight, and the net force is zero, at this point acceleration has gone away. The rock is no longer speeding up. It stops speeding up That is, it maintains a constant speed from then on through the rest of the fall. The velocity has reached a maximum velocity, and we call that velocity terminal velocity. Anytime an object is moving through some medium that, gas or liquid, that applies a drag force, there might be a terminal velocity if the thing moves long enough. Just one reminder of a couple things here. The net force is in the same direction as the acceleration that it produces. And here you've got a lot of net force, so you've got a lot of acceleration. Here the net force is smaller, so you've got less acceleration, but you still have some acceleration. And here you've got just a little bit of net force, so there's just a little bit of acceleration. And finally, at that point where there's no net force, there's no acceleration. And of course, the rock is falling, so the velocity is down. And reminder, anytime acceleration and velocity point the same direction, right, they're both pointing down in this case. Anytime velocity and acceleration point in the same direction, that means the object is speeding up. And keeps on speeding up until it reaches a terminal velocity, a maximum speed. Now let's look at one other example involving some drag force. This case, a drag force through water. Let's say you're fishing and you've got a fish on the line. You're trying to pull the fish up, and close to, you're standing on a dock while you're fishing, and the fish is close to the dock, so you end up pulling the fish straight up. Here's the fish, and there's the line pulling up on the fish, and we know that this upward pull is 50 newtons, and we weigh the fish after we pull it out of the water, and find that the mass of the fish was 3 kilograms. We found that as we pulled the fish up in the water, it was harder to pull. But once the fish got out of the water, it was easier to pull. That means that while the fish was in the water, there was a drag force on the fish. The pulling force, while the fish was in the water, the pulling force had to work against both the fish's weight pulling down and a drag force pointing down. As you pull the fish up, the fish's velocity is up, but then of course drag force always points opposite to the fish's velocity, and we'd like to find the magnitude of that drag force. The magnitude of that drag force in the case where the fish was being pulled up at a constant velocity. Now remember, constant velocity means just pick any 2 points in time and you'll measure the same velocity at those 2 times. So change in velocity between any 2 times is 0. So acceleration is 0. Acceleration measures the rate at which velocity is changing, and the rate of change of velocity in this case is 0, no change at all. So we want to find a force. We know something about the acceleration, so we use the same use the same approach as we saw last time. That is, first identify all the forces and their directions with a free body diagram. So the forces look like this. There is, of course, weight, which is mass times g, pulling down on the fish. There's the tension in the line pulling up on the fish. And then there's a drag force also pulling backwards on the fish. And there's no acceleration. The fish is moving at a constant velocity. No acceleration means no net force, because if there were a net force, there would be acceleration. Net force causes acceleration. And we always want to know which way is which way is positive, which way is negative. So let's say the fish is moving this way, the fish's velocity points this way. So let's say that again the direction of motion is the direction of the positive direction. Up is positive here, and down is negative. So we take all that information and turn it to an algebraic statement. We want some kind of an algebraic expression that shows how those forces combine to produce the net force. Net force is just all the upward force minus all the downward force. All the force in the positive direction minus all the force in the negative direction. The only force in the positive direction is tension. And then the forces in the negative direction are weight and drag force. And we'd already figured out that the net force is 0, so that combination of forces must add up to 0. All the upward force exactly balances out all the downward force. Now we put in the numbers and we can get a number for the strength of the drag force. Net force is the tension minus weight minus drag force equals 0. The tension, I said earlier, was 50 newtons, and then the weight is a mass of 3 kilograms times g, acceleration due to gravity, 9.8 meters per second, minus drag equals 0. 3 times 9.8 comes out to 29.6. So here's 50 newtons minus 29.6 newtons. Mass times acceleration is a force, and force has the label of newtons. Minus drag force equals 0. So 50 minus 29.6 is 30.4. And 30.4 minus the drag force is 0. So the strength of the drag force itself, the magnitude of the drag force, is 30.4 newtons, or we should round that off to just 2 digits because the numbers that we input into the calculation had only two significant digits to them. So we'll say it's about 30 newtons for that drag force. Now let's look at one more example, this one dealing with friction. In particular, this will be a question about static friction. Let's say you've got a truck on a just parked on a sloped road. The slope is inclined at 7 degrees. So here's horizontal, and here's the slope, 7 degrees, and then here's the back end of the truck, the 2 tires at the back end. and then there's the rear of the truck, and there's the license plate. And the truck is just sitting there. Now, of course, if something is on an incline, it could slide downhill, but it's not sliding downhill. That means there's static friction preventing the sliding. And we would like to know, what is the magnitude of that static friction force? And furthermore, we find that if this car had been tilted just any more than that, at a greater than 7-degree angle, the car or the truck would slip downhill. Static friction can be strong enough to prevent sliding if this is the angle of inclination, but it can't be strong enough to prevent sliding if the angle is any steeper. That is, right now at this point here with the 7% angle, the maximum possible amount of static friction is being applied from the road to the tires on the car. So a larger angle means they're sliding, but that means that the value of the static friction force is the maximum possible value of the static friction force. Remember that a static friction force can take on any value up to some maximum value, and the maximum value is just a coefficient of friction. This Greek letter mu here means a coefficient of friction, and subscript s for static, times normal force. And this is always the normal force that's coming from the same surface that is applying the friction force. So this is the normal force from the parking lot surface on the truck. All right, we would like to know what that maximum value of the static friction force is. So same deal. We're going to figure out what all the forces are, and then write an expression that shows how those forces combine to give you a net force, and we can use that to figure out the unknown force that we're looking for. So first, what are the forces? It's a little bit more complicated in this case because the truck is on an incline. There's still the weight pulling straight down like it always does. And then there's a normal force from the parking lot surface pushing on the truck. Normal force is always perpendicular to the surface, but the surface is at an angle here. So when the normal force from this surface is perpendicular to that surface, the normal force is pointing at a diagonal, not straight up. Like that. And then the only other force is the static friction force. If this truck were sliding, it would slide downhill. When static friction is preventing sliding, it points opposite to the slide that it is preventing. So preventing downhill sliding means there's an uphill static friction force. Okay, now we want a coordinate system. Again, we want to know what's positive and what's negative. In this case, we're going to do the coordinate system a little bit differently because things aren't just vertical and horizontal here. If the truck were moving, it would be moving downhill along this line. So if there were motion, that would be the direction of motion. So let's make that the downhill direction, the positive x direction. And then in an xy coordinate system, y is always perpendicular to x. So then y will be the y-axis, the positive y-axis will be perpendicular to the surface of the parking lot. In other words, it'll be in the same direction as the normal force. Okay, now let's see what, well, the one other thing to say here, of course, is that the truck has a constant velocity, constantly zero. It's not moving. But the important part is not so much the value zero. The important part is that that velocity, which happens to be zero, is constant, because constant velocity means no acceleration, which means no net force. So that tells us that the net force is zero. If the net force is zero, that means both components of the net force must be zero. The x component, the downhill component of the net force must be zero, and the y component, this component of the net force, must also be zero. So static friction, that's the thing we're trying to find. That's one of the forces that points along the x-axis. So when we write down the expression that shows how things combine to give us the net force along the x direction, that's going to be one of the terms in our algebraic expression. So net force along the x direction is what we need to think about. And as always, net force along the x direction is all the force in the positive direction minus all the force in the negative direction. Here's the positive direction. There are no arrows, force arrows pointing in the positive direction, but there is positive force along the x direction. There's an x component to the weight, and that x component of weight does pull in the positive x direction downhill. Let's take a closer look at that. Here's the actual weight vector, and remember, you should always think of a vector and its components as if they were the hypotenuse and the two perpendicular sides of a right triangle. So here's the vector, that's the hypotenuse, and one component of that will be the downhill component, the x component of the weight, and the other component of that will be perpendicular to that, right? Two components of any vector are always perpendicular to each other. That's the y component. And the y component of the weight is pointing that way. In other words, it's in the negative y direction. The x component of the weight is pointing that way, downhill. In other words, in the positive direction. So the net force along the x direction is all the force in the positive direction, which is the x component of the weight, minus static friction, which is pointing in the negative x direction. But that has to add up to zero because there is no net force. We can write this in terms of things that we know. First of all, we can figure out this angle. This angle here is just going to be the same as the angle at which the parking lot is inclined. So let's draw it this way. So there's the parking lot, 7-degree angle. Here's the weight force, and here's the x component of the weight, here's the y component of the weight, and let's see, let me just draw this a little more carefully here. Right, the y component of the weight has to be perpendicular to the x component of the weight. So that means the y component of the weight is perpendicular to the parking lot surface. So now, here's a triangle right here. This side, and this side. Three angles in a triangle, remember your geometry. Three angles in a triangle have to add up to 180. There's 90 degrees, 7 more degrees. So that angle there has to be 83 degrees. 83 degrees plus 7 is 90 degrees, plus this other 90-degree angle gives us 180 degrees. So that angle is 83 degrees, which means make a vertical line that will be perpendicular to this line, and then think about this angle here, which is 90 degrees. 83 degrees gets you from here to here. 83 degrees gets you from here to here. And then this must be 7 more degrees from here to here in order to have a 90-degree angle between this line and this line. So this angle here is 7 degrees, which is just the same as this angle right here in this part of the triangle. Right, this angle here is the same as the angle of inclination. Go back to chapter 3, section 3 in chapter 3, where the authors go through exactly this same argument. But in any case, the important part is that now we know this angle, and this component of the weight, the x component of the weight, is what we want to find. The x component is opposite to the angle, to the 7-degree angle that we know. Whenever you want to figure out the length of a triangle side that's opposite to some angle you know, you use sine. The side of the triangle that's opposite to your angle is equal to hypotenuse times sine. Hypotenuse is just the magnitude of the force itself, the weight, m times g. And hypotenuse times sine of 7 degrees in this case, gives us the size of the x component, the side of the triangle that's opposite to our angle. So this, the x component, is just the weight itself times sine of 7 degrees. Remember, that's the maximum value of the static friction, because if the slope were any steeper, the truck would start to slide. And this, as I just said, was mg sine 7 degrees. And since this minus this equals 0, then this has to have the same size as the maximum static friction force. And in this case, we knew the mass of the truck. The mass of the truck was 4,000 kilograms. So mass of 4,000 kilograms times g, the acceleration from gravity, that's 9.8 meters per second, times sine of 7 degrees. That'll be a fairly small number. That's going to equal the maximum possible value of static friction for this case. And so what kind of numbers do we come up with here? 4,000 times 9.8 times sine of 7 degrees, that comes out to, if we just round it to 2 digits, because we have only 2 digits of information in one of our inputs, comes out to about 4,800 newtons. Maximum static friction. So that's how that works. You may have noticed in the reading that there's an important similarity in all types of friction force. Right? The static friction, the kinetic friction, and the rolling friction are all involve the magnitude of a normal force and a coefficient of friction. That coefficient of friction is our way of measuring exactly how sticky any pair of surfaces are. Different pairs of surfaces will have different values for their coefficient of friction. Say a really rough piece of sandpaper and a piece of wood would have a large value for coefficient of friction. A much finer grain of sandpaper and that same piece of wood would have a smaller value for their coefficient of friction. And you'll deal with this a lot more in class.